All right, we'll get started. So the next topic we want to cover is what we call as linear discriminant functions or Fisher's linear discriminant function. So let's see what's the idea here and what is it that we want to do. Suppose we have a function gx which is a linear function. And this function has a property that if we evaluate this function for a vector x, and if vector x happens to come from class C1, the function produces a value which is positive. On the other hand, if function x represents an example from class 2, then this function gx produces a value which is negative. So if we had such a function, obviously one could use such a function to perform classification. That is, you plug in the component values of vector x into the formula for gx and see if the result is positive or negative. All right, and accordingly make a decision. Since this function can be used to perform classification or to do discrimination between different examples coming from different classes, we call such a function as a discriminant function. And since it is a linear function, so we call it as a linear discriminant function. All right. And one way to express such a linear discriminant function is to express it as W transpose X. So where X is a vector, W is a vector, both the vectors are of the same size, then what we can do is we can take W transpose X and calculate that product. And that will be a scalar number, could be positive, could be negative, and we could use that to do the classification. All right. So question is, how do we get hold of this weight vector W? Yes, please. No, we are not talking of probability here.
And now this one is based on certain linear functions which will classify into these two approaches are. Like how do we really decide which approach?
Well, basically, that's a good question. As I said, every approach has its own limitations and advantages. And you can think of different approaches as tools in your toolbox. Okay. And after some practice, some experience, you start relying on certain tools more than the others. All right. So in general, for every situation, maybe there will be more than one possible option for you to pick a classification model. Ultimately, which one will you pick? Will depend on your experience, your liking, and things like that. All right. That's number one. All right. Number two, naive Bayesian basically, as I said, is a linear classifier, makes the assumption the features are independent. All right. In this case, we do not make that assumption, number one. And number two, again, this also is a linear classifier, but it has certain properties that you will see as we go along. Okay. And then based on that, you can decide whether you want to use this one or that. All right. And of course, we're going to look at few more. So basically, it's just a question of what ultimately is, you end up like. All right. So question is, how do we figure out this weight vector W? And there are a number of different ways of choosing that weight vector W or learning that weight vector W given a number of examples. All right. The method we are going to look right now is known as the method based on Fisher's criteria. All right. So let us see what is Fisher's criteria and why we may want to use this. All right. So let's just recap again linear discriminant functions, as I said. All right. Now, if I didn't write when you have a linear function, typically it will have a constant term also, or bias term, typically what people call it. All right. So in a most general form, your linear discriminant function gx can be written as W transpose x plus W0. All right. Suppose you take two examples or 2 points or two vectors, x1 and x2. Now remember, in a two-dimensional space, when you talk of a linear function, the linear function is specifying a line. All right. In a three-dimensional space, a linear function specifies a plane. In a higher dimensional space, a linear function specifies what we call as a hyperplane. So plane in higher dimension. All right. So let us say that we have 2 points, x1 and x2, that lie on the hyperplane specified by gx. All right. In that case, this relationship W transpose x1 plus W0 equals to W transpose x2 plus W0. And if you do a little bit of manipulation here, you end up with W transpose times x1 minus x2 equal to 0. So basically what this equation tells you is that the weight vector that we are going to be looking for is going to be normal to any vector lying in the hyperplane. All right. And as I said, instead of hyperplane, you can think of lines in 2 dimensions. All right. So let's look at what we are trying to do here, or what does the Fisher's discriminant function. So let's take an example from 2 dimensions. We have points from 2 classes, blue dots and red dots. All right. And in the left hand part, I show you a weight vector W with a thick line. All right. So that is the direction of weight vector. So basically, if you draw a line in that direction in 2 dimensions and project all the black and red points on that line, basically you will see a mixture of red and black points spread on that line. All right. If you change the orientation of weight vector W and look at another orientation, another direction for weight vector W, shown in the right hand side, and draw a line and again project all the points. Okay. So what you're going to see here is a different mixture of red and black. All right. So basically, if you imagine rotating this weight vector W around the origin, looking at different directions and doing projections for different directions, it's possible that there might be a projection which will show a property where most of the red points are on one side of the line and most of the black points are on the another side of the line. And there is a nice gap between these 2 sets of projected. All right. And if we can do that, then we can use that projection as a way to perform classification. So basically, what the Fisher's criterion does is that it tells you how to find such a weight vector such that when you do the projection of data on that weight vector using normal projection, then if you are working with two classes, then your data will have a fairly good separation. All right. So let us say that y sub I is the projection of your ith example, and that projection is given as W transpose X sub I. Remember, over here and in most of the equations that you will come across, the constant term W0 is always absorbed in the weight vector W, and we never generally write that as separate. All right. It's just for the convenience sake. All right. So it's in there. All right. So yi is the projection of ith example xi through a weight vector W. All right. So let's look at all the examples that we have from two classes and do their projections. And once you have done their projections, let us take all the examples from class 1 and calculate their mean value or mean projection value. Similarly, take all the examples from class 2 and calculate their mean projection value on the line. All right. So M1 hat or M1 tilde minus M2 tilde difference square divided by S1 tilde square plus S2 tilde square. So M1 and M2 are the means in the projection space, and the corresponding variances are given by S1 tilde square and S2 tilde square. All right. So let's look at this criterion function JW. For these projected points to be far away from each other, what you will like to do is, or what you like to have, is that the numerator M1 minus M2 square should be as large as possible, because the two means should be far away from each other. All right. So you want the numerator to be as large as possible. How about the denominator? You don't want the variances to be large, because the means might be far away, but if the variances are large, there will be still overlap. So you want to minimize the overlap. That means you want variances to be small. So you want numerator to be large, denominator to be small, with the result that you want J of W to be as big as possible. So you want to maximize this criterion function. So basically what you want to do is you want to find a weight vector W which will maximize this criterion function. All right. Now, we are not going to go through the derivation, how one can derive such a weight vector through few steps of doing optimization or maximization. All right. What we are going to do is to define the scatter matrices, which actually I had defined earlier. So basically what we have done here is just, shown them again. And if you look at the right hand corner, that is where you see the formula for the weight vector W, which will maximize the Fisher's criterion function. So given a collection of training examples coming from two classes, if you want to project them using Fisher's criterion function, you need to pick a weight vector W that is given as SW inverse multiplied with M1 minus M2. All right. So this is the Fisher's criterion, and we have skipped the actual derivation of this, but this is the end result achieved. All right. So let's look at a simple example here, how you can use this. So basically, we have a company, it hires its customer service reps using 3 skill tests. So they get a candidate, they run the candidate through 3 tests, and the test score lies in the interval of 0 to 10. All right. And what the company has is a record of last year's scores and the employees who were hired and how well they have done. All right. So basically, we have scores on 3 tests, or you can say there are 3 features. And then there is a corresponding label, good or bad, whether if somebody with those scores did a good job or they did a bad job. All right. So basically, that's what we have. And now you get a new candidate and you run the candidate through the test. And the candidate scores 5, 5, and 6 on these 3 tests. So question is, based on all that information that you have, should we hire this person or should we not hire this person? So you can answer this problem by using Fisher's linear discriminant function. Of course, you can answer it by some other methods also. But what we'll do is we'll try to answer this using Fisher's linear discriminant function. All right. And we will carry out these calculations using Python. All right. So basically, you can say we have an array of feature vectors. So that array is there for good, and then we have an array for feature vectors labeled as bad. And what we do is we calculate the mean. So we have the mean vector for training examples representing good employees and mean of training examples representing bad performance. Then we calculate this S1 and S2, those are scatter matrices, as we have defined in the earlier sheet. So we get them, and then we get the total scatter matrix, which is S1 plus S2. So we are doing all the calculations that we need to do. And now we need to calculate the inverse. All right, so remember the formula is SW inverse multiplied with M1 minus M2. All right, so we got the scatter matrix, we calculate its inverse, and then we do the multiplication to get the weight vector. So basically, we get the weight vector, and what we can do is once we get the weight vector, we can calculate the projected means for good performance and projected mean for the bad performance. All right. And we can take a middle point between those two means and say that that middle point is going to be our cutoff point for good and bad. All right. So basically, the employee that has been tested, we plug in that employee's numbers and we get a result 4.43, which happens to be closer to the mean of bad performers rather than closer to the mean of good performers. That means we should not be hiring this person. All right. So that's how Fisher's linear discriminant function gets applied and can be used to build a classifier. All right. Now remember what Fisher discriminant function is doing it is projecting the points. I showed you the example with 3 features, but it could have been with more features. But ultimately, you are projecting them on a line. All right. So in some sense, you are doing dimensionality reduction. In this case, you are just reducing the dimensions to 1 for a 2-class problem. All right. So what one can do is one can look at what is the difference between PCA and Fisher's linear discriminant function. So on the left-hand side, I show you a collection of data points and show you how PCA will be applied or what are the two axes that PCA will figure out. All right. On the right hand side, I show you what the Fisher's linear discriminant function will do and how it will figure out the corresponding weight vector. All right. So in one case, in the case of PCA, the idea of class label is not there. It is just trying to approximate the data. But in Fisher's linear discriminant function, we do take into account the class labels. That means when you are doing the dimensionality reduction, you are taking into account class labels. Your reduction is being done not for approximation, but reduction is being done for classification. So it is a supervised way of doing dimensionality reduction. Now you might say, well, if I'm going to do the dimensionality reduction and if I have more than two classes, what do I do? So I'm going to leave that for you to read. But essentially what you do in the case of multiple classes, if you have m classes, then you find m minus one weight vectors. So basically you need then more than one weight vector. So you find m minus one weight vectors, again through the use of those scatter matrices. And instead of taking just the largest eigenvalue of those scatter matrices, you take a couple of other eigenvalues and eigenvectors similar to what you do in PCA. And you end up with, dimensionality reduction. So here is an example that shows you how you can do that. And again, you can go to this blog post and take a look at all the details that are shown there in terms of how to apply Fisher's linear discriminant function for two classes as well as for multiple classes, and look at it from a dimensionality reduction point of view. All right. So just to summarize, as I said, FLD is also known as linear discriminant analysis in some cases. It can be used for more than two classes. For m classes, you will be needing m minus one projections. The underlying assumption here is features are independent and are normally distributed. But again, what people have found through empirical studies is that the difference when the features do not satisfy these conditions are not much. All right. And finally, the PCA finds the axis with maximum variance for the whole data set, while LDA or Fisher's linear discriminant function tries to find the axis for the best class separability, because it's not the data approximation, but the separability that is important. And in practice, one can perform LDA followed by PCA for a dimensionality reduction. Okay, so both are possible. So with that, I think we will stop here.